Okay, in the first part here of the section 2.6 notes, we're going to recover two things that we've already talked about in chapter 1, vertical and horizontal asymptotes. And then later in these notes, we're going to discuss a new type of asymptote called a slant or oblique asymptote, and then finish up with limits of rational functions. And this is all designed to help us with what we're going to do a little bit later on today, which is graph rational functions by hand. So a vertical asymptote occurs whenever the denominator is equal to 0. And so whenever you are looking for vertical asymptotes, the first thing you're actually going to do is you're going to simplify by factoring and then canceling anything that the numerator and the denominator have in common. If something in fact cancels out, then the x value associated with that factor is what we call a removable discontinuity. And we, if you remember, talked about this in the section 1.2 notes, wherever I said, if you plug in an x value and get 0 over 0, we called that a removable discontinuity, or you'll also hear me use the terminology of a hole. And so if you simplify by factoring and something cancels out, that is not a vertical asymptote. It is in fact a hole or a removable discontinuity. And we'll see the difference in those as we work the examples here in these notes, and then graphically once we get to the Rady method a little bit later on. Okay, so here in example 1, we want to just identify the vertical asymptotes and or any holes that the function might have. And so here for letter A, we have x over x squared minus 9. And the first thing I notice is that that denominator can be factored as a difference of squares. And so I'm going to go ahead and factor it. The next thing I would try is to cancel anything that they had in common. But this function does not have anything in common, and so nothing cancels out. Therefore, to find my vertical asymptotes, I'm going to look to the denominator, and the denominator cannot equal to 0. So that means I'm going to have two vertical asymptotes. And really, when we write these, I'm going to back up here. We don't write x cannot equal to. We actually write x equals to, because a vertical asymptote is a vertical line. So I'm going to write x is equal to 3, and then x is equal to negative 3. I would also accept this, and you'll also see this sometimes written x equals plus or minus 3. And then holes, well, nothing canceled out, and so therefore this function does not have any holes. Okay, letter B, you're going to see something slightly different. So in the numerator, I have x plus 3. The denominator, just like letter A, is going to factor into x plus 3 and x minus 3. And so now I see that something is going to cancel out. The x plus 3 and the x plus 3 will cancel, and so that's going to give me a hole with an x-coordinate of negative 3. And the reason I know that it's negative 3 is because the factor that canceled out is x plus 3. And so now when I simplify this further, and I'm going to go up here to do that, it's going to give me 1 over x minus 3. And so to find the y value of the hole, because the hole is really just a point, it's an ordered pair. And so now I'm looking for the y value of the hole. I'm going to substitute negative 3 back into the most simplified version. And so if I substitute negative 3 into this simplified version right here, I'm going to get 1 over negative 3 minus 3, which will reduce to negative 1 over 6. Okay, so now are there any vertical asymptotes? Well, if there are any factors left over in the denominator, you've got to set those equal to 0 to get your vertical asymptotes. And so I see that I have this x minus 3 factor left in the denominator, which means I'm going to have a vertical asymptote at x equals 3. Okay, in example C, again, you're going to try to factor anything that you possibly can, but in this particular example in letter C, notice that you can't factor anything. And that's especially true about the denominator because of that plus sign. If it was x squared minus 4, then that would factor as a difference of squares. But since it's plus 4, that doesn't factor at all. There's nothing you can do in the numerator And so the only thing I could even possibly have here is a vertical asymptote. But if you set the denominator equal to 0, what you're going to end up getting is imaginary. And so therefore, there is no vertical asymptote for that particular function. And there's no whole because nothing canceled out after you factored. Okay, letter D. Notice that the denominator can be factored since it's a trinomial. I need factors of -12 that will add to +4. And since the lead coefficient is 1, I can shortcut the factoring here. And so this is going to be x plus 6 and x minus 2, I believe. And nothing there is going to cancel out. And so both of the factors in the denominator are going to give me vertical asymptotes at x equals +2 and -6.